Okay, we're good. We're good. All right, 3-4. Instantaneous rate of change. Okay, that's what the derivative is. It is saying at this very moment, at this very instant, how are things changing? Because when we talk about regular slope of lines, what are we talking about? We're talking about average. It's the same all the way around. But you can't do that with a curve. But you can take it at some particular instance and say, what's the slope at that point, at a tangent? And it really has to do with this, all that limit stuff. We're not kind of using that anymore, but that's what that is. Okay? So let's look at this example. The area, can you guys see that at the back? The area A of a circle is related to its diameter by the equation. A equals pi over 4 times the diameter squared. It's not an equation that we see a lot. How fast does the area change with respect to the diameter when the diameter is 10? Whenever you're asked about how fast is something changing, we're talking about a rate, we're going to be talking about a derivative, usually. Okay? The rate of change of the area with respect to the diameter is, that means take the derivative of this thing. So I wrote dA dt, means the derivative of the area with respect to the diameter is. Remember, pi over 4 is just a number. So 2 times pi over 4, and then times the d, and the d squared went to plain old d. Does that make sense? And then that becomes what? Pi over 2? Because it's 1/4 times 2, that's 1/2. Where did this 2 come from? Okay, think about this. We've got pi over 4, and then we've got d squared. Now think about how we were doing the derivative. 2 times pi over 4, so that's right there. D, take 1 away, that's a 1. Okay? And so just kind of simplify that to pi d over 2. We had to get that general thing of a derivative. Now, when d is 10, the area is changing with respect to the diameter at the rate pi over 2 times the diameter, which we know is 10. So it's 5 pi meters per second meter. They're going to have that unit for you. Okay? And then they might expect you to go ahead and do 5 times pi, and you would get 15.71. The whole point of that little example was to say, okay, we got to take the area of the derivative of this thing, and it's just a formula, A equals, that's got some numbers and a variable. Do it just like we've been doing. Does that make sense? Okay. And then some of these are just some definitions, but you can get these if you want to print the notes. Velocity is the derivative of position. So that's the first derivative. Velocity is the first derivative. And it tells how fast and what direction you're going. If it's positive, you're going forward. If it's negative, you're going backwards. So that's velocity, first derivative. Speed is the absolute value of velocity. And so think about a speedometer. Whether you've got the car in reverse and you're going 90 miles an hour, does it show negative 90? No, it's absolute value of that number. It's always positive. So your speed is always positive. So, absolute value of the velocity. I hope you're not going in reverse 90. But that's and okay, so we're there. Acceleration is the second derivative. It's the derivative of velocity. Okay? So this is like second derivative of that position. So you have a position, take first derivative, that's velocity. Second derivative, that's acceleration. And that's the rate at which velocity is changing. And it shows how quickly whatever it is picks up or loses speed. And you also have sudden change in acceleration is called jerk. Okay. How many of you have had physics? Those of you that probably had calculus in high school were also taking the physics. Did you use your calculus to help you with your physics? Yeah. I remember taking engineering physics, and at the same time I was taking Cal 2 and Cal 3. And I only survived engineering physics because I had the Cal 2. Oh, and then you go, oh, well, I wish I'd had that. Yeah, for sure. Okay. All right. Here's an example. Dynamite blast blows a heavy rock straight up with a launch velocity of 160 feet per second, about 109 miles per hour, and a figure that I don't have. It reaches a height of s equals 160t minus 16t squared feet after t seconds. And then they ask you 4 questions. So let's see if we can work through this question. I think I've got it already written out on this example, so let's talk about it. All right, the instant the rock is at its highest is, the one instant when velocity is 0. Does that make sense? Because it's when it's stopping and turning around, coming down. So when velocity is 0, you're at your highest point. Okay? That makes sense? All right, so to find the maximum height, you could do a couple of things. You could throw that in the calculator and you could find the max, but we're using our calculus here. Find when v equals 0. Well, v is the derivative. So we're going to take the derivative of our original. Here's a position. Take the derivative of it and set it equal to 0. Solve it, and you get time is 5. What does that tell me? That after 5 seconds, I'm at the highest point. So how am I going to find out? Did it ask when? No, it said how high does the rock go? That's what it asked. So what do I have to do? Plug 5 in for the original there. 160 times 5 minus 16 times 5 squared, and you get 400 feet. So after 5 seconds, this thing is up 400 feet, highest point. So we use the idea that velocity, when it's 0, you're at your highest point. Okay? Does that make sense? Now, second question, and I'll go back so you can copy. What are the velocity and speed of the rock when it is 256 feet above the ground on the way up and on the way down? We need to find t values, time values, when the height is 256. Okay? So set the equation equal to 256 because this is height. Set it equal to 256. Bring that 256 over, or bring everything else over here. Factor it. Now I factored out 16 to start with, just to make it easy. Okay, you want to always do that. Factor out anything you can. Get it down to something that factors easily. Okay? Okay, so we've got 2 and 8. What are we going to do with those? Okay, plug it into the derivative, into the velocity. So v of 2 is the same as s prime of 2. And have we found s prime? I don't think we've done that yet, have we? We did it up here, right here. So we're going to plug 2 into this. So s prime of 2, blah, blah, blah. So 96 feet, that's moving up. And when you plug in the 8, you get negative 96 feet per second. That's moving down. And so those would be your 2 answers for that part of the question. We good? Okay. Third part of the question, do I have it written? What is the acceleration of the rock at any time during its flight after the blast? What is acceleration? Second derivative. So we have to take the derivative of this guy. What's that going to be? Negative 32. Okay, feet per second squared should be. Okay, and that's at any point. Negative 32 feet per second squared. And then the last part of the question, When does the rock hit the ground again? When does the rock hit the ground? Well, it's on the ground when the height is what? 0. And it's like that when it starts, and it's like that when it ends. There's 2 places. So, if you set the original equal to 0, factor it out, you get t is 0, t is 10. Well, it can't be this answer. That's at the start. So, 10 seconds, it's back on the ground. Okay? That ought to get us ready to do these. I think I have 5 problems. We'll see. Very much. Nope. Okay. All right, so we just did that. Let's see. This is a little bit different. A body moves on a coordinate line so that it has a position, and here's your equation. Can you see that? On the interval, 0 is less than or equal to t. T is between 0 and 9. That's the interval we're on. With s in meters, t in seconds, and they ask us 3 questions. Find the body's displacement and average velocity. Find its speed and acceleration at the end points. And when, if ever, does the body change direction? So, do we know what displacement is? Not really, it's not a derivative.
That's actually like ending distance minus the initial.
So it's really like the change in the y values. If you were thinking about average change, it's the y values on the top. So it's really f of 9 or, f of 9 minus f of 0. Let's do that. So f of 9 is going to be what? And really, I should use s. Okay. The body's displacement, we're going to call that delta s. And so it's s of 9 minus s of 0. I'll let you figure out what that number is. What'd you get? 18. So for the displacement, that's delta s, and you're just going to do s of 9 minus s of 0. The body's average velocity, what is that going to be? It's not a derivative because it's average. It's not instantaneous velocity. So what are we going to do? It's average. It's like the slope thing. So we found the top. What's the bottom? 9 minus 0. Because this is like s of 9 minus s of 0 over 9 minus 0. That's what they're asking us to do. So we already have the top part. The bottom part is 9 minus 0, which is 9. 18 divided by 9 is 2. So that's the average. Okay. All right. Speed at the left and right endpoints. Well, what is speed? Absolute value of velocity. Okay. So speed, absolute value of velocity. So we're going to have to take velocity, find the velocity of this. What is velocity? 2t minus 7. Okay. And so then what do we do? We've got to find v of the endpoints. So we need v of 0 and v of 9. So we get negative 7 here. And what's 9? 11? Okay, but what do we need to remember? Absolute value. So we're going to have 7 and 11. Okay, are we good? All right, acceleration at the left and right endpoints. What's acceleration? Second derivative. Well, the derivative here is 2t minus 7. What's acceleration? 2. So it's going to be 2 here and 2 here. There's no variable. Okay. When, if ever, does the body change direction? What did we say about when something's moving? When does it change? When v is 0. When v is 0. So, where's our velocity? Here? Okay, so take that, set it equal to 0, and solve it. Okay, just to be sure, you want to test on either side of it, and if there's a sign change, then there's a change in direction. Okay, so what am I gonna test? Here's the way I like to do it, and we'll certainly get into this when we get to maxes and mins. There's 7 halves. What's something on the right of it? Here's 9 at the end, and here's 0. Pick a number here. 4. Okay, and pick a number here. 1. Okay, so we're going to plug these into what? Which function are we plugging them into? Right here? Because we said we're talking about wind velocity. So we're dealing with that. So this is v of 1 we want to figure out, and v of 4. v of 1. What's the sign when we plug in 1 right here? Negative? And what's the sign when you plug in 4? Positive. Okay, so there's indeed a change in direction. So you would want to show that. Okay? All right. Questions on that one?
It says when,
Do what?
how many seconds?
Oh, that's the 7 halves that goes there. Okay. We just verified it with this, Jeff. Okay. All right. So this is another one just like that one. So you try it and see if you can get all the answers. This is about displacement, exact same questions. Let me move it up. Here's the function. Can you read that at the back if you guys don't have it? T cubed minus, well, I'll just write it bigger. So your interval is between 0 and 5. This is your function. You're asked for the displacement, average velocity, speed. So kind of just go through the same stuff that we got. Let's see what you get.
I can give it money.
We'll continue that. Are we coming up with those answers? You are when you're writing them down from the board? Okay. Are they making sense? Move up a little bit. Oh, you're just doing good. Okay. Can I move up a little? This last part's a little different as far as the answer that we had gotten before. That makes sense on E? Because we did the same thing. It changes direction when velocity is 0, but when you set it equal to 0 and you factor it, you get t is 5. That's at the end of the interval, so it's not going to matter because we're at the end. Go up. That far? Or more? Okay. Yes. Just I don't know why those sometimes print weird. Yeah. Okay. So we're good. You kind of know, and if you've had physics, the displacement, the velocity, all of that stuff should begin to ring a bell. If you haven't, it's going to take a little longer to get it, but they are definite applications for what we're doing. Everybody good? Can I go back? Or are we still writing? Dinah, you still writing? You ready? You sure? Okay. All right. So that one, we're good. All right. This is a shorter one. Maybe. Number 3. Bless you. The equation for free fall, bless you, at the surface of a celestial body. Sounds really great. In outer space is S equals 5.91 t squared. How long does it take a rock falling from rest to reach a velocity of 27.1 meters per second? What do you think we do? Okay, Drew said find the derivative, set it equal to 27.1. Does that make sense? So what is the derivative? What is S prime? 11.82 t, and we're going to set that equal to so what's t? And it says round to the nearest tenth. So do that division. 2.3?
Oh, wait, no.
2.3.
Yeah. That won't work. Okay, so that's not a bad problem. You did have to think about what am I going to do? I need velocity. I'm going to take the derivative, and I'm going to set it equal to 27.1. Okay. Number 4 is exactly like the example we did that we went through, but we should try it again. And at one point, we're going to have to use our calculator. So we should go through this one. Okay, here's the equation. 20t minus 0.8 t squared. Find the velocity and the acceleration. So what are we going to get when we do that? We got first derivative and second derivative. So velocity is what? 20 So that's v. And then the acceleration is the second derivative, and what do we get? Okay, so that's acceleration. How long does it take the rock to reach its highest point? What did we say that occurs when? Okay, occurs when v equals 0. So here's v. So solve that. $12.5. Okay, how high does the rock go? What do? Here's the height. That's the height. How high does it go? Well, when it gets to its highest point, it took 12.5 seconds. What do we do with that? Plug it into the s function. So s of 12.5 equals, I have to get back up there so I can see it, 20 minus 8 times 12.5 squared. 0.8, sorry, thanks. That didn't even look any better. 125. Okay. And I think the unit is there. It's meters. Okay. All right. How long does it take the rock to reach its half of its maximum height? Well, what's half of its maximum height? 62.5. And so what do? The original has to equal that height. 62.5 equals, what was that original? 20t minus 0.8t squared. Okay, that looks kind of ugly. Not like it's going to factor. This is where your calculator comes in. So I would bring these two guys over. You would have 0.8t squared minus 20t plus 62.5 equals 0. As long as you've got that, you can throw it in the calculator. Go to y1, put this in. Instead of t, you got x. And find the two x-intercepts. So find that. Do you know how to do that?
Would it be plus 62 or minus 62?
I brought these guys over.
Okay.
Depends on what you did.
You did the other way on that.
It should be the same because then these two would be these signs rather than these. But when I do it, I always put that in y1. And in y2, I put 0 because that's just my shortcut way to find intercepts. And then you can just do second calc 5, enter 3 times, and you've got it. Let's see what you get. Do what? Be really difficult. I mean, because you're going to get decimal answers with 2 decimals it says to round, but it's not something you're going to factor. You could do the quadratic equation and you would get them. Yeah. You'd still want a calculator when it got down to that last radical, probably. Okay, what do we get? Rounded to 2 places. Yes. Okay. All right. So we're getting the idea how to use this. What's the last question? How long is the rock aloft. What does that mean? How long is it in the air? Well, what did we say? It's on the ground when? Till when? So we've got to set that position thing equal to 0 and solve it. There's 2 times. That second time is how long it stayed in the air. So take that original thing and set it equal to 0. You guys are letting me do the work. Now, could you also put that one in the calculator and find it? You could. If you had to do this one by hand, I would want to get rid of that decimal. I guess that's what I'd do. Oh, no, I don't know what that is. But I'm going to let you do it in your calculator and get it.
Could you factor out t, and your t, 1t would be equal to
1t
0.
is equal to 0. It will be.
The other one would be 20 minus 0.8 t.
Mm-hmm. So solve that one. What do we get? 25. Okay. Even though there's only 5 problems, these are taking a little bit of time. You got one more. Hang in there. One more. Okay. All right. There's 2 questions here. The volume V equals 4/3 pi r cubed. That's the formula for volume of a sphere. Of a spherical balloon changes with the radius. Would that make sense to you? As the radius gets bigger or smaller, the volume changes. Okay, at what rate does the volume change with respect to the radius when r is 2? At what rate is it changing? We need to find the derivative.
I think this on homework 31 is the exact question.
It was? I think it was an area question, not a volume. But
There was volume.
was it? Okay. But was it already taking the derivative? Like this?
That's the only way that's how I solved the problem. I didn't know how to solve it.
Okay. If you find that one, or I'll look, but find it and print it and show me. Show me. Okay. So we got to take the derivative of this. So I'm going to write that here. V equals 4/3 pi r cubed. All of this is a number. So what do we get when we multiply? 4 pi r squared is V prime. Is that right? Okay, and then what do? It said, what's the rate when the radius is 2? Plug in 2. $16 pi, and it says leave your answer in pi. So 16 pi here. All right, then it says using the rate from part A, by approximately how much does the volume increase when the radius changes from 2 to 2.3? Okay, we've already said this is how the volume's increasing in relationship to R. If R is changing from 2 to 2.3, what do we need to think here? How do we need to think through that?
It's the change. If you plug it in 2.3, then minus that.
Well, when R changes by, how much did it change here from 2 to 2.3? 0.3. The volume changes 16 pi for every 1 unit. So what are we going to multiply 16 pi by? 0.3. And they want a decimal answer. So go ahead and do that for me. What do we get? Did it say? And it said round to 2. So that's good. Okay? Got to think about what it's asking you to do. Okay? All right.